Hi, welcome again. I'm Neil. This chapter is all about rotation, rolling, torque, and angular momentum. Now, the concepts of rolling, torque, etc. are really underestimated. You could not leave a room if it were not for the concept of torque. You couldn't turn the door handle. The door wouldn't roll on the hinges. Axles on a car wouldn't propel the car forward. So virtually everything works on the concept of torque. Rolling, rotation, angular momentum are all consequences of motion. Here is a picture of the Earth. If you've ever wondered why the Earth is rotating on its axis, not just the Earth, mind you, all planets, all stars, all moons, everything in the natural world that exists in the cosmos rotates about some axis. Why? Well, rotation is nature's way of bringing stability. It's a natural mechanism for stability. So the Earth, if it did not rotate on an axis, would lose a lot of its stability, and the consequences will be quite severe. That's a conversation for another chapter, however. So today we're going to focus on the equations of motion that relates to things moving in a non-linear form. So let's take a look at the chapter at hand. And what we will do, what we have done, is derive the equations for objects undergoing angular motion. So all of our measurements are going to be based on the unit of the radian, not the degree. It's the unit of the radian. You know, their rotation can be measured in revolutions and degrees and radians, etc. But the equations are derived in terms of the radian unit of measure. So angular velocity, angular acceleration, angular displacement are all measured in terms of the radian. If we were to scroll down and compare side by side, these were the equations that were derived, the linear equations for motion that were derived in Chapter 1 on kinematics and projectile motion. Here are the angular equations. They are identical in form. All we've done really is switch out the linear parameters for their angular counterparts. For example, v for linear velocity becomes omega for angular velocity. S for linear distance becomes theta for angular displacement, so on and so forth. A for linear acceleration becomes alpha for angular acceleration, and so forth. So it's the same equations we've already derived in prior chapters that we can apply to angular motion. So in this chapter, we talk about from first principles how we come up with the concept of things not moving in a linear form. These are what these diagrams are showing, and the components of acceleration for objects that are moving in a circular manner. There are two components. There's a tangential component and there is a radial component. It's the addition of those two components that gives us the net acceleration, and that's what all of this derivation is about. And there are multiple examples. There are countless examples that we can come up with for measuring rotational rates to use these equations that we have just derived for angular measure. This is on my trip to Croatia, overlooking the Adriatic Sea, the town of Split. There was a restaurant on there which I found fascinating because it was owned by the same family for generations, and you had to pre-order your meal 24 hours in advance of actually going to the restaurant overlooking the coast, and it seats just a few people at a time. You can see why the view is really fantastic. And so the third generation owner of the restaurant was kind enough to give a tour of how they do things the old school way. And here's this good-looking pig over here being rotated on firewood and coals and slow cooked, for many hours. It's one of the reasons why you need to pre-order your food the day before. Came up with a great example of that rotating pig to calculate some dimensions of angular coordinates. We came up with angular displacement and linear displacement and some other properties of measurement just based on that pig that was being cooked. So it gave me something to do with the long wait while I looked at this pig here. It was quite delicious, by the way. Meat fell off the bone, as they say. This is in the Amazon jungles of Ecuador. The indigenous tribes, they served up, and it's one of my treks to the Amazon jungle. The indigenous tribes, they cooked up some beetle larvae. They're essentially worms. They're about yay long, about 2 to 3 inches long, and they're very, very plump. And they're being grilled over here. It took quite a bit of effort to decide how I was going to get this into my mouth and down my throat. I did it, because I've learned the hard way. You don't say no to indigenous tribes. So any indigenous people that offer you their food, it's not a good thing to say no, in particular in their country, when you're at their mercy. So I ate it, and I didn't like it, but I pretended I did. So we came up with an example of these beetle larvae being skewered. It's amazing the things you can come up with as physical examples of things that are being used in everyday life. So we talk about determining angular measure, and we've actually used forces here with the coefficient of friction to determine whether certain things are going to happen with these beetle larvae on these skewers. It's quite an interesting example that I think I came up with for this particular problem. Kinetic energy of rotation. So much like the kinetic energy of the center of mass of linear motion, there's also the counterpart here, which is the kinetic energy of rotation. So we derive the kinetic energy of rotation, and from that stems the concept of the moment of inertia. Moment of inertia is analogous to mass in linear measure. Mass is a resistance to change. It's a measure of inertia, linear inertia. Moment of inertia, it's a measure of the resistance to rotation, if you will. And so we've segued into determining this new parameter called a moment of inertia. And we can write now the total kinetic energy of an object that's both moving linearly and rotating in terms of its kinetic energy of translation plus its kinetic energy of rotation. So this is the complete expression for the kinetic energy of an object that's undergoing both linear and rotational motion. How do we calculate the moment of inertia? It sometimes gets quite complicated. We will limit ourselves to a certain situations where the mathematics and the integrals are doable for this particular level of physics that we're talking about. And I've calculated, as an example, I've taken several objects, common objects like a disk, for example, and I've derived the moment of inertia for a disk, and I've used that to calculate the moment of inertia of things like a sphere, like a solid object like a ball, for example, that's rotating, and the resistance of motion that ensues. The derivation can be somewhat lengthy, as you can see here, but the reader will have all the time in the world as they go through the chapter in detail, and quite a bit can be learned from this derivation. So moving along with the concept of rotation, as we move from Croatia back stateside to Ocracoke Island off the coast of North Carolina. This is believed to be the final resting place of the most infamous pirate of them all, Edward Teach. The reader might know him as Captain Blackbeard. It's believed that in the 1700s, the British Navy, they beheaded Captain Blackbeard, and somewhere on this island is there's a mass grave with the headless body of Captain Blackbeard. But in the event, there's a lighthouse on this island, which it's quite cylindrical, and it made for a perfect example on my visit there. I know I did not find Captain Blackbeard's body. That warrants a second trip. What if the tower were to unfortunately tumble over? Can we calculate the speed, the angular speed, and the linear speed of an unfortunate soul that might be standing on the top of this lighthouse here? So it's an example of things that tend to tumble over. So it's a great example for architects, for example, when they're building towers and things that they ought to consider. Another prime example, this is taken in Oregon, one of the wind farms, the many wind farms out in the west coast of the United States. That generates a lot of electrical energy for the grid system. The rotation of the shaft produces kinetic energy, and in the form of rotation, which can be used to generate electricity. So we did an example, a very realistic example of how much power can be expected with a certain minimum wind speed for these windmills to generate some power. And that brings us to the concept of torque. Like I said, torque is it's a force that causes rotation or leads to rotation. And without a concept, understanding of torque, you'd be hard pressed to leave a room because you couldn't turn the door handle. There'd be no torque that would exist. Torque comes from the Latin word which means to twist. So there are numerous examples. We've done several of them, and in the use of torque and the calculations of torque. Here is on one of my treks to the African safari. This is out in the Serengeti of Tanzania. And this is a Maasai warrior. Of all the pictures that I've taken around the world, I've been to all 7 continents on the planet. This is arguably the most famous picture I've ever taken of a Maasai warrior walking through what's called Ngorongoro crater, which is a volcano. Just happened to be walking by and I caught a picture of the Maasai warrior. And this is what goes on in the neighboring surroundings here. I caught 2 cheetahs early one morning on a kill of a wildebeest, and there's one cheetah that's trying to rotate, twist, or to create a torque on this wildebeest to get to the underbelly where the meat is softer so it can bite into. So it was quite fascinating to stand there and watch these 2 cheetahs. Here's one resting in the shade. Tried to turn this wildebeest over. They were having a hard time because the cheetah weighs only a fraction of the wildebeest. The wildebeest was still alive, by the way. It was trying to run away, and the cheetah wouldn't let it. So it was quite disturbing yet fascinating to watch nature run its course. This is in the close to the Arctic Circle in the very far north of Sweden. It was so cold that day that even the ski lifts were frozen solid. So I thought that was fascinating in its own right, but with the additional weight of all the frozen ice on the different lifts, I created a problem to solve for how much weight each of the load-bearing posts on either side of the hill that's holding up all of these ski lifts with the additional weight of all of the frozen ice would have to support. So it's quite a realistic example. As we can see as we draw the diagram and look at all different torques acting, I think the reader will get quite the understanding of how the application of torques works in the creation and the building of things like bridges, for example, and ski lifts. So it's quite an entertaining example. And finally, we finish off with the topic of angular momentum. Much like linear momentum, there's a concept of angular momentum. That is to say, as an object is spinning, it wants to keep spinning unless there's an external force to cause it to do otherwise. The best example of this is an ice skater. As an ice skater is spinning about one spot, she can tuck her arms in, and what that does effectively is redistribute her mass about the axis of rotation, and it causes her to speed up. If she puts her arms out, and again redistributes her mass about her axis of rotation, and it causes her to slow down. So the conservation of angular momentum is of paramount importance. It's one of those laws, just like the conservation of linear momentum and the conservation of energy, that as far as we know, it is not violated anywhere in the universe with the exception of inside the event horizons of black holes. So it's a very, very powerful law, and several examples of the conservation of linear momentum have been worked on. This is one of my treks treks to the far north when I crossed into the Arctic Circle in the far north of Norway. This is the other end of the world. This is the southernmost city of the planet, Ushuaia. It literally means the end of the world in Argentina. So this is the far north in the Arctic Circle. This is the far south in Argentina, in the town of Ushuaia. And this is right in the middle. This is in Ecuador. This is actually separating the northern and southern hemispheres of the planet. This is the equator. So here's the actual marker. I've got 1 foot in the northern hemisphere, 1 foot in the southern hemisphere, in the northern hemisphere. So these 3 pictures, what do they have in common? Well, it's all to show a very specific example. 3 different places of the world, very, very far apart. Close to the North Pole, close to the South Pole, and me at the equator. So it was quite a trek to get to all of these places, but it serves for a fantastic example. And the example is the calculation of the rotational speed. You see, every object that is rotating has 2 velocities to consider, the linear velocity and the angular velocity. Now, the angular velocity is the same no matter where you live on Earth, at the equator or at the poles, because it takes the same amount of time to move. Everyone moves 360 degrees in the same amount of time. But the linear velocity is different depending on where you live. If you live close to the equator, you've got a bigger circle to move around in 24 hours, as opposed to living close to the poles. You've got a smaller circle to go around the rotational axis, but you've got 24 hours, so you can afford to move slowly. So everyone's linear speed is different depending on the latitude which you live, and this is exactly what this problem is all about. And here's a calculation for the linear speed in the Arctic Circle close to Norway, the calculations for the angular speed in Ushuaia close to the South Pole, and finally the calculation at the equator, smack dab on the equator. And so the reader will find something very, very interesting, how significantly different the speeds of rotation are if you live close to the equator. And so we put all of that together to end up with a concept of rolling. Rotation plus linear motion, as this diagram depicts, gives you rolling, much like the wheels of a bicycle as they roll down a hill. And we can calculate what the total energy is for rolling, and derive an expression for the acceleration of the center of mass, much like a bicycle that's allowed to coast down a hill. And here's an example of just that. This is taken in the Andes Mountains in Bolivia on one of my treks down there. This is called the Youngest Pass, so the locals call it the Death Road. It's the most dangerous road in the world, responsible for most deaths on the planet. I did a mountain bike trek down the Death Road, the Youngest Pass. Not a whole lot of braking going on here because it's just a lot of loose rock. So I pretty much spent about 50 miles worth of coasting down this hill, just hoping not to go off the edge and fall into the abyss over here. It's about 15,000 feet, no, it's about 5,000 meters above sea level. I'm sorry, about 3,000 meters above sea level, about 15,000 feet would be the equivalent. So we created an example of the acceleration of the center of mass of those bicycle tires as I coasted my way down the Death Road, the Youngest Pass in Bolivia. So it's a lengthy chapter, but I think the reader is going to have a solid understanding of the concept of torque, rolling, rotation, and angular momentum at the conclusion of this chapter. And once again, I thank you for your time.